Summer of 1945 found me standing in the New Mexico desert at a place we called Trinity, watching a light brighter than any sun humanity had ever witnessed turn the sand beneath it to glass. That moment changed how I understood energy, and what I grasped in that flash is something they still fail to teach you when you flip a switch and watch light fill your room. You believe you understand energy, electrons flowing like water through a pipe, and that explanation is exactly where your understanding falls apart. A question haunted me long before the Manhattan Project, long before Los Alamos, long before the world learned what physicists had uncovered. Burn a log in your fireplace and ask yourself where the warmth originates. Carbon combining with oxygen, you might answer, releasing heat as it reacts. That explanation works on one level, but push deeper and ask what actually happens at the scale of the atom when that flame dances before you. For all of human history, we borrowed energy from the sun, energy stored in chemical bonds, in the arrangements of electrons around atoms. Babylonians burned wood, and Romans burned wood, and Victorians burned coal, and for 10,000 years every civilization on earth borrowed the same energy, stored the same way, released by the same chemistry. Fire, we called it, and progress. But this energy was always a pittance, a whisper, even when it seemed vast to us. Children playing with matches, that is what we were, never suspecting that inside the atom itself lay a furnace of staggering magnitude. Once you grasp what holds the nucleus together, and what happens when that hold breaks, the world will never look the same to you again. Consider the atom as your teachers described it, a nucleus at the center with protons and neutrons huddled together like seeds in a fruit, electrons orbiting at comparatively great distance. Your teachers told you the electrons were the interesting part, that chemistry concerns itself with electrons, how they pair and share and leap from one atom to another. True enough, as far as it goes, but that explanation misses the deeper question entirely. Each proton in the nucleus carries a positive charge, and as your earliest physics lessons taught you, like charges, repel with considerable violence. Two protons crammed into that impossibly small nuclear space experience, electromagnetic force pushing them apart with tremendous fury. Grasp what that means, and you realize the nucleus should explode, that every nucleus and every atom in your body and in this room and in the stars themselves should be flying apart at this very instant because electrical repulsion demands it, and yet nothing explodes. This mystery consumed the greatest minds of my generation, the question of what holds the nucleus together, what force could overpower the electromagnetic repulsion between protons and keep that nucleus intact. Picture a Gothic cathedral holding itself up, and ask what invisible flying buttresses prevent the stone from collapsing, knowing something must be there, even though you cannot see it. When the answer came, it revealed that we had been standing at the edge of an ocean without knowing it. James Chadwick discovered the neutron at Cambridge in 1932, a discovery that earned him the Nobel Prize 3 years later. Before that moment, we imagined the nucleus as a collection of protons alone, somehow bound together against their will. And the neutron explained much by adding mass without adding charge, and suggesting that whatever held the nucleus together operated between all nucleons, protons, and neutrons alike. The real breakthrough arrived when we began weighing things very carefully. Take a proton, its mass known to extraordinary precision. Then take a neutron with the same precision. Then take a helium nucleus, what we call an alpha particle, containing 2 protons and 2 neutrons. Simple arithmetic suggests the helium nucleus should weigh exactly as much as 2 protons plus 2 neutrons, and that arithmetic turns out to be wrong. The helium nucleus weighs less, as if 4 people entered a room and somehow only 3.97 people remained, the missing fraction not leaving through the door but becoming the heat in the room. Strip away the abstraction, and that is what Einstein's equation actually means. Einstein enters our story here, though he would later wish he had not. E equals mc squared tells us that mass and energy are equivalent, the same thing viewed from different angles, mass being concentrated energy and energy having mass, the relationship governed by the speed of light squared, which represents an almost incomprehensibly large number. When protons and neutrons came together to form a helium nucleus, they released energy, a vast amount relative to the particles involved, and that released energy took mass with it. The nucleus weighs less because it gave up some of itself to the universe in the form of binding energy. Sit with what that means for a moment. We call that mass difference the mass defect, and it represents the energy required to tear the nucleus apart, measuring how tightly bound those nucleons are, quantifying the strength of whatever force holds them together. That force, we came to understand, is the strong nuclear force operating only at nuclear distances, making electromagnetism look feeble by comparison, hidden from us until we learn to peer into the heart of matter itself. Compare electromagnetism to a firm handshake, and the strong force becomes a grip that can crush diamonds. And that is where the story transforms from physics into destiny. Not all nuclei bind with equal strength, and plotting binding energy per nucleon against atomic mass reveals a curve that should haunt anyone who truly grasps it. I drew this curve 1,000 times on blackboards from Berkeley to Los Alamos, showing how light nuclei like hydrogen and helium bind relatively loosely, while heavier elements show increasing binding energy per nucleon. Nucleons packed more efficiently and held more tightly as the curve rises. But then something curious happens around iron, specifically iron 5,6 at 8.8 MeV per nucleon, where the curve reaches its peak with the highest binding energy per nucleon of any nucleus. Beyond iron, the curve descends, meaning heavier nuclei like lead and uranium and plutonium bind less tightly per nucleon than iron does. Consider what this means in terms of energy, because the curve functions as a map, and all paths lead downhill toward iron. Combine very light nuclei into heavier nuclei moving toward iron, and you release energy because the products bind more tightly and the difference in binding energy gets liberated. Fusion. We call this process the reaction that powers the sun and lights every star in the night sky, burning continuously for 4.5 billion years above our heads. But another path exists. Split very heavy nuclei like uranium into lighter fragments moving toward iron, and you also release energy because the fragments bind more tightly than the parent nucleus and the difference gets liberated again. Fission. We call that process. Both paths lead downhill energetically and both release energy, and for most of human history both remain theoretical curiosities, interesting ideas with no practical consequence whatsoever. December of 1938 changed everything. In a Berlin laboratory where the shadows of war were already gathering, Otto Hahn and Fritz Strassmann were bombarding uranium with neutrons, searching for transuranium elements, heavier elements created when uranium absorbed a neutron and transmuted. What they found baffled them completely. Barium showed up in their results with an atomic number of 56, when uranium has an atomic number of 92, and you cannot create barium from uranium by adding a neutron. Creating barium from uranium requires splitting the uranium nucleus roughly in half. Hahn could not accept his own results, so he wrote to his longtime collaborator Lise Meitner, who had fled Nazi Germany just months before, a Jewish woman escaping persecution and carrying the knowledge of atomic physics in her mind while leaving everything else behind. Meitner and her nephew Otto Frisch spent the Christmas holiday in Sweden, walking through the snowy forest near Gothenburg, working to understand what Hahn had observed. Their realization came that the uranium nucleus, after absorbing a neutron, had become unstable and begun to oscillate and elongate, stretching like a liquid drop under surface tension until it pinched in two, electromagnetic repulsion between the protons in the two halves driving them apart with tremendous force. Frisch suggested calling the process fission, borrowing the term from cell division in biology, a name from life science for a process that would come to define death on an unimaginable scale. News spread across the world's physics departments. Within weeks and within months, we understood that fission releases not just energy, but additional neutrons, 2 or 3 neutrons for every uranium nucleus that splits, neutrons that could in principle cause additional fissions, a chain reaction, in other words. Think of a chain reaction as an infection of instability. Each fission, a sneeze, that sprays neutrons into the surrounding material, the reaction's fate determined by the same mathematics that governs whether a virus becomes a pandemic or burns out in a village. One infected person or one split nucleus can lead to 2, then 4, then 8, then millions, or it can lead to nothing at all. I remember when this became clear to us, and the implications hit immediately as both obvious and terrible. Sustain a chain reaction, and you release energy on a scale that makes all previous human energy sources look like candles in a hurricane. And we knew that the Germans understood this too, because everyone in physics understood it. Let me make concrete what we are discussing, because the numbers themselves constitute a kind of revelation. Burning carbon, whether coal or wood or gasoline, releases roughly 4 electron volts of energy per atom. And that 4 electron volt figure represents the scale of chemical energy, the scale of electron rearrangement, the scale of every fire ever lit by human hands. Fissioning a single uranium-235 nucleus releases approximately 200 million electron volts. Not 200, but 200 million, and this represents not a different technology, but a different order of reality. Nuclear energy exceeds chemical energy by a factor of 50 million, meaning all the coal ever burned by humanity combined with all the oil ever extracted and consumed together represents less energy than exists in a modest quantity of properly configured uranium. Picture a piece of vintage orange Fiestaware, those ceramic plates colored with uranium oxide glaze that sat in American kitchens throughout my lifetime, and the energy released by fissioning the uranium in that single plate would power a typical house for a decade. Fire in the heart of matter, that is what we discovered, and like our ancestors staring at their first flames, we did not fully grasp what we held. Chain reaction physics is not complicated, but the subtleties matter enormously, because those subtleties would determine whether nations lived or died. When a uranium-235 nucleus absorbs a slow neutron, what we call a thermal neutron, it becomes uranium-236 inches, an excited state, and this excited nucleus is unstable. Fission occurs within an inconceivably small fraction of a second, the nucleus splitting into two fragment nuclei of unequal size, while releasing energy, and, crucially, releasing 2 or 3 additional neutrons. A key question consumed us at Los Alamos concerning what happens to those neutrons. Some escape the material entirely, while others get absorbed by non-fissile materials like impurities and structural components. And the uranium-238 that constitutes more than 99% of natural uranium. Others get absorbed by uranium-235 nuclei and cause additional fissions. Average fewer than 1 neutron per fission, causing another fission, and the reaction dies away. Subcritical, a spark that fails to catch. Average exactly 1 neutron per fission, causing another fission, and the reaction continues at a steady rate, critical, which is what a reactor needs for controlled and sustained energy release. Average more than 1 neutron per fission, causing another fission, and the reaction grows exponentially. Supercritical, precisely what a weapon needs, but only for an instant, a runaway chain reaction that releases its energy before the material can fly apart. Geometry determines the outcome, along with purity and the presence of moderators that slow neutrons to the thermal energies at which fission becomes most probable, all depending on critical mass, the minimum quantity of fissile material needed to sustain a chain reaction. The 2nd of December 1942 brought the first controlled chain reaction, achieved by Enrico Fermi in Chicago, beneath the abandoned stands of Stagg Field, the Manhattan Project's first great achievement and proof that theory could become reality. Graphite moderated the neutrons while control rods of cadmium absorbed them as needed, and withdrawing those rods sufficiently made the reaction go critical, a self-sustaining nuclear chain reaction controlled by human hands for the first time in history. I received the coded message afterward, though I was not there that day. The message reading that the Italian navigator had landed in the New World. A new world indeed, though whether it would be a world of abundance or annihilation remained unclear. That coded message haunts me still, and I ask myself why we spoke in riddles, knowing the answer is that we had already begun understanding that knowledge itself had become dangerous. Science that had always been open and published and shared across borders had become a weapon. The information in Fermi's reactor functioning simultaneously as a blueprint for power plants and a blueprint for bombs, inseparable, because the binding energy curve does not come with a moral selector. Consider what the binding energy curve tells us about the future. How heavy nuclei like uranium sit on the descending right side of that curve and split into fragments with mass numbers around 90 and 140 that sit closer to the peak. Binding energy difference converts to kinetic energy of the fragments, to gamma rays, to kinetic energy of the released neutrons. Roughly 80% of the energy appears as kinetic energy of fission fragments, highly charged and moving at perhaps 3% the speed of light, colliding with surrounding atoms and transferring their energy as heat, which is how a nuclear reactor generates thermal energy that boils water and turns turbines and generates electricity. But another consideration makes nuclear energy different from chemical combustion in a way that matters deeply. Mass conversion is real and measurable, and fissioning 1 gram of uranium-235 completely means the products weigh less than the starting material by about 1 milligram. Multiply that milligram by the speed of light squared, and you get approximately 23 megawatt hours of energy from 1 gram, 1 milligram of mass, converted entirely to energy. Generating that same energy from coal requires burning roughly 3 tons. 3 tons of coal versus 1 gram of uranium, and the coal leaves behind ash and carbon dioxide and particulates and sulfur compounds accumulating in our atmosphere and changing our climate. Uranium leaves behind fission fragments that are radioactive but contained in a quantity you could hold in your hand. Let this transform how you think about energy itself. Because we had always assumed energy was something consumed and depleted and borrowed from stored chemical bonds. Nuclear fission revealed that mass and energy were interchangeable, and that tiny amounts of mass, properly liberated, represented almost unimaginable quantities of energy. Carbon we burn accumulated over millions of years from ancient sunlight, while uranium we fission was forged in seconds during the explosion of a star that died before our sun was born. Stellar ash, that is what we are burning, releasing energy that waited billions of years for this moment. Fission involves splitting heavy nuclei, but the binding energy curve points toward another possibility that we understood even then without being able to achieve it. Fusion represents that other path. Hydrogen, the lightest element, has its single proton sitting at the far left of the binding energy curve with relatively little binding energy per nucleon. Combine two hydrogen nuclei, two protons, and you move rightward on the curve toward greater binding energy with the difference released. A difficulty arises because those two protons repel each other electrically, requiring tremendous energy to push them close enough for the strong force to take over and overcome electromagnetic repulsion. Temperatures exceeding 10 million degrees are required. Stellar temperatures, and the sun fuses hydrogen into helium in its core, precisely because core temperature and pressure are high enough to force protons together against their mutual repulsion. In a weapon, and I speak of what came later, what I oppose but could not prevent, fission explosion provides the temperature and pressure to ignite fusion, creating the hydrogen bomb, the thermonuclear weapon, a fission device serving as trigger for a vastly more powerful fusion reaction. Edward Teller's vision realized after I had already begun arguing against it, and the Atomic Energy Commission would later revoke my security clearance, partly because I questioned whether we should build such devices at all. The binding energy curve pointed the way, and we followed it into a future I sometimes wished we could not see. But let me return to the essential point, because losing it in details of bombs and reactors and politics and personalities would be easy. What we discovered about nuclear energy was not merely a new power source, but a revelation about the nature of matter itself. Every object you touch and every breath you take and every star you see in the night sky is held together by the strong nuclear force, containing binding energy locked within its nuclei that dwarfs anything we had previously imagined. Glass in your hand and air in your lungs and ground beneath your feet, all of it is frozen energy, mass concentrated by forces operating at distances we cannot directly perceive. We did not create this energy, but merely found a way to release what was always there, coiled like a spring inside every atom since the universe began. I read the Hindu scripture, the Bhagavadgita, at Berkeley in the original Sanskrit long before the war, and gave copies to friends because I found in it something Western philosophy could not provide, an acknowledgement that we are swept up in forces larger than ourselves and that our choices operate within constraints we did not create and cannot escape. The Gita speaks of dharma, of duty, of obligations that fall upon us by virtue of who we are. Arjuna, the warrior prince, does not want to fight because the battle array before him contains his teachers and his kinsmen and his friends, and he sees the destruction that must follow and recoils from it. Krishna tells him the cosmic order is not his to refuse, that the battle will happen and the destruction will come whether Arjuna participates or not, that his duty is to act rather than concern himself with the fruits of action. When the Trinity device was tested and that fireball rose and expanded and the light resembled 1,000 suns bursting into the sky at once, I remembered a line from that scripture, the one you know. Triumph was not what I felt, but recognition that we had become instruments of something far larger than our individual intentions. 3 weeks later, work at Los Alamos translated Fermi's controlled reaction into the uncontrolled fury of the bombs that fell on Hiroshima and Nagasaki, 200,000 dead or more, cities erased, a war ended, a new era begun. Touching the binding energy of the nucleus changed what it meant to be human. Energy exists inside every atom, indifferent to what we do with it, capable of warming cities or annihilating them, generating electricity for 1 billion people or rendering the earth uninhabitable. Physics operates as a terrible democracy because the laws do not distinguish between purposes, and the binding energy curve offers itself equally to the reactor and the bomb, chain reaction proceeding according to mathematics with indifference to whether it is controlled or catastrophic. What we discovered was not good or evil but true, and truth once uncovered cannot be covered again. Sometimes I think about a future I will not live to see. Fission fuel is not infinite, but it is abundant beyond any previous energy source, and thorium, which can be bred into fissile material, is even more plentiful than uranium. Fusion, if we can learn to sustain it and bottle a piece of the sun, would draw its fuel from the hydrogen in seawater, effectively unlimited. Today, at facilities like ITER in France and the National Ignition Facility in California, scientists pursue what we only dreamed of: sustained fusion that could power civilization without the shadow of the bomb. Small modular reactors promise to bring fission power to places that could never afford traditional plants, and the binding energy curve still points the way forward. Energy sufficient to power human civilization for as long as humans exist without depending on burning fossil carbon or poisoning the atmosphere that all life depends upon, that is the promise. But the same physics that makes this possible makes the weapons possible too, with knowledge of enrichment and critical mass, and chain reactions spreading despite efforts to contain it. The International Atomic Energy Agency works to contain what cannot truly be contained, and you cannot have one without the other because the binding energy curve does not come with a moral selector. I tried to explain this to politicians who thought they could somehow separate the peaceful atom from the military atom, but there is no separation, only physics and our choices about how to apply it. Tonight, when you turn on a light, consider what you are actually doing. Somewhere in a reactor, uranium nuclei are splitting and neutrons are moderating and chain reactions are proceeding at carefully controlled rates. Binding energy that held those nuclei together for billions of years, since they were forged in the explosion of a star that died before our sun was born, is being released as heat transferred to water, turning steam through turbines, spinning generators, sending electrons through wires to your home. That light in your room is powered by mass being converted to energy, not much mass. A few atoms per second with the mass defect accumulating invisibly, but real mass undergoing real conversion, Einstein's equation made manifest in the fixture above your head. Nuclear energy is what this is, what we discovered, what we are. Matter is frozen energy, and nuclei are bound by forces that dwarf electromagnetism, and the binding energy curve is a map of creation and destruction alike. We did not invent these truths but uncovered them, and uncovering them meant inheriting a responsibility that previous generations could not have imagined. Physicists have known sin, and we cannot unknow it, and the chain reaction proceeds. Whether humanity will use this knowledge wisely remains the question. Whether you will choose the reactor over the bomb, whether the binding energy that holds the universe together will become in your hands a tool for human flourishing or an instrument of annihilation. Physics cannot answer that question because it belongs to all of us, every human being navigating a world transformed by what we learned about the heart of matter. The energy was always there, waiting, and we found it. And now you must decide what you are.